integration examples that start with partial fractions. You should watch these videos on partial fractions before continuing with this video. So we have a fully factorized denominator. So this factor x plus 1 gives rise to this partial fraction, and this factor x minus 2 gives rise to this partial fraction. So now we're looking for a single fraction on the right hand side with the same denominator as the left hand side. So we get this, and then we can say that the numerators must be the same, they must be equal to each other because the denominators are the same. So we get this equation equating the numerators, and then by substituting values in for x we can work out the values of a and b. So when x equals minus 1, a is equal to 2, and when x equals 2, b is equal to minus 1. So we substitute these two back into the a and b here, and we get these partial fractions. Now we need to integrate this fraction, but we already have the partial fractions for this, so instead we're going to integrate these terms. We have a constant over a linear function for each, so we get natural logs when we integrate, and then we add on the constant of integration. We can combine these two into a single log term, so we need to get rid of this coefficient first, so we bring it up here as a power and then use the division rule for logs. This term is positive, there's a plus here, so the x plus 1 squared will go into the numerator. This is a negative term, so the x minus 2 goes into the denominator like this. The modulus is necessary if we have limits of integration to use. If not, we can use normal curved brackets. Example 2, we have a repeated factor in this, the x minus 2 squared, so we get 3 partial fractions. I've skipped out the first few steps. These are just the numerators equated to each other, and then substituting in x equals minus a half gives a equals 2, x equals 2 gives b equals minus 1, x equals 0 gives c equals 3. So now we have all three of these values. So substituting the values in, we get these 3 partial fractions. So if we have to integrate this fraction, instead we'll integrate the partial fractions. So we have a constant over a linear function here and here, so we get natural logs from these two, but this is a constant over a quadratic function, so we do not get natural logs here. So we rewrite the middle term there as minus x minus 2 to the power of minus 2, so rewriting this as ax plus b to the power of n. That's what I've done here. Doing the integration, so here I've got ln 2x plus 1, then I'm dividing by the coefficient of x, which is 2 there, and I'm multiplying by that 2 here. And for this fraction here I have ln x minus 2. If I divide by the coefficient of x, which is 1, that doesn't do anything, so I don't need to put that in. I'm multiplying by 3. For x minus 2 to the power of minus 2, we increase the power by 1. We divide by the new power. We divide by the coefficient of x, so that's 1. I can put that in here, it's not going to do anything. And then simplifying, add on the constant of integration. We can combine these two log terms. It's not necessary, but we can if we want to. So this 3, which is a coefficient, we need to get rid of that, bring that up here, and then if I use the multiplication rule for logs, we get these terms. Okay, this example, it's something that's not worth copying if you're taking notes here. So fully factorized denominator, so it would appear as though we would get these 2 partial fractions, but just watch and see what happens. Okay, so common denominator, so a single fraction on the right hand side. If I now equate the numerators, because the denominators are the same, we get this. And there's a problem here. A and B are just constants. Yeah, they're just the coefficients here. And then you've got linear functions of x. So on the right hand side of the equation here, we will get something that's linear in nature. We're not going to get something quadratic. So these two cannot be equal to each other. So where does this problem arise? The problem is right at the beginning. There was an issue here. If you look at the degree of x for the numerator and the denominator, we have a quadratic expression in the numerator and it's quadratic also in the denominator. So degree 2 and degree 2 again for the denominator. The numerator should have a degree of x which is lower than the denominator to do this, to make your partial fractions. It must be lower. So if the denominator is quadratic, the numerator should be linear or just a constant. So this is an issue at the moment. What we should have done is we should divide right here. We should do long division, division of polynomials, before we start. Okay, so the numerator degree, if it's more than or equal to the denominator degree, divide polynomials first. Take this example. We want to integrate, so we're thinking perhaps partial fractions first. However, they're both quadratic. The degree of the numerator is equal to the degree of the denominator. Yeah, you've got x to the power of 2, degree 2, x to the power of 2, that's degree 2. They are the same, so some division first, and then rewriting this in a useful form where you've got the quotient here plus the remainder here divided by the divisor. Now let's ignore the 1 plus for the time being, we'll add that in later on. This fraction here, fully factorize the denominator. Now we have a quadratic denominator and a linear numerator. So the numerator has degree 1, the quadratic part, the denominator, has degree 2. So that's now good, that's correct. Partial fractions, equating numerators. I've missed out some working out here, but a will be 1 and b will be minus 2. So we're going to integrate all of these terms. I'll put the 1 in again there. And this has given us these two partial fractions. And then we integrate and add on the constant of integration. And both of these two terms are constants over linear functions, so we get natural logs. Or we can combine the two log terms into a single log term. For practice, try these questions.